Welcome. This is lecture number 34. In this lecture, we are going to talk about PID controller design and tuning under voltage mode control with MATLAB case studies. So, here we are going to talk about first PID controller structures and functionality, then overview of PID controller tuning methods, then PID controller tuning using stable pole zero cancellation, then PID controller tuning using transient specifications, and the limitation of PID controller in switch mode power converter. So, first we want to talk about a PID controller, which is a very well known controller in the context of control system. In the PID controller, if we take an ideal PID controller, it is a parallel realization. So, we have a proportional gain which is Kp, proportional gain, integral gain which is Ki, and a derivative gain which is Kd. Okay? This is a standard PID controller, and if we express this PID controller into polynomial numerator and denominator polynomial form, so this is the structure, and then we can separate out Ki because we want to write in this form where the coefficient in the numerator we want to keep without, that means the constant coefficient we want to write in terms of unity. Okay? Because for power converter in the previous lecture, what we did that we all the time numerator and denominator we wrote in this form where the constant term was written in terms of unity by suitably scaling it. Next, this PID controller has 2 0 1 pole, but this is not physically realizable because we know that this is an improper transfer function. We need at least 2 pole, 2 0 means there should be at least 2 poles. Okay? Now, introduction, and we will discuss this in actual PID controller reality. We cannot implement an ideal derivative. So, there will be always a band limited derivative where we need to consider a derivative filter, that means a low pass filter, and this comes typically when you use an op amp. The op amp itself has a finite bandwidth that is coming into the picture, that comes into the picture. Now, introduction, the practical PID controller, we need to add a derivative filter as we discussed, and this derivative filter comes in this structure where tau d is the time constant, and typically this time constant is much faster if we want to realize closely like a derivative action depending upon the type of system we are considering, because this should be much smaller than the time constant of the system. Then 1 by tau d is a high frequency pole that we are introducing, and typically due to band limited emit of the op amp, this by default comes, but even we can set this pole much lower than the actual op amp bandwidth. So, that means this can be even lower bandwidth than the bandwidth of the op amp, because we even can see that if the op amp has 200 megahertz bandwidth and your power converter is 1 megahertz, then 200 megahertz is too high. So, this derivative action can inject various high frequency noise into the system, and that is not desirable. Sometimes we deliberately add a high frequency pole for noise attenuation, that I told, that means it can be much smaller than the actual bandwidth of the op amp. So, now a practical PID controller, I think this can be written as with a derivative filter in this structure, that means in the pole 0 structure in numerator and denominator coefficient form, where again we can write our standard notation, that means all the time we try to write the constant term should be unity by suitably scaling. So, here we took out Ki. So, whether it is a ideal PID controller or a practical PID controller, this DC gain of this PID controller always is your, that means your Ki in this case, but yes, you have an integrator. I am saying that the constant term which is taking out is the Ki. So, here we can write that how can this can be mapped with this coefficient, and that will lead to this mapping between K1, K2 with the Kp, Ki and Kd and tau d. Now, structure of PID controller. So, PID controller, whatever we discuss is a parallel PID controller, and of course, this is with a derivative filter, but we can also consider a series PID controller in which we can consider a simply PI control and a PD control in cascade, and that can be transformed into a PID controller, and where this coefficient can be mapped and it can be obtained Kp Ki from this K1, K2, K1 dash, K2 dash. So, it can be a function of this. That means, Kp Ki Kd will be a function of K1, K1 dash, K2, K2 dash, and it can be function of tau d. So, PID controller functionality, that means we talked about parallel PID controller, series PID controller. Sometimes PID controller is also written like this, PID in the parallel form. It is also sometimes we can take Kp out, then we write 1 plus 1 by Ti, the time constant, into 1 by S, that is the integral term, plus Td, which is a derivative term, into S. So, this also is another form, and of course, there is a derivative filter, it is there. So, we can take Kp out and then we can write in terms of the integral time constant and the derivative time constant. This is also another way of representation where Kp is common, okay. And this type of structure is used particularly for Ziegler-Nichols tuning, where the Kp can be obtained from the critical gain, and then the timing parameter like integral timing, this integral time as well as derivative time constant, those can be found from their suitable tuning rule. So, PID controller functionality. PID controller, it has 3 action. One is the proportional, which link with the proportional term, proportional. Then I stands for integral, it stands for integral, and D stands for derivative, and their respective gains are Kp, Ki and Kd. Now, if we do not change Ki and Kd, if we increase Kp, that means if we increase Kp, then overshoot will increase, percentage overshoot, because we will see that if you draw the Bode plot, frequency response, if you simply increase the proportional gain, in most of the cases that your gain plot will simply go up, and as a result your bandwidth can increase, but this can also reduce the phase margin, because your phase response may not drastically change, and that can reduce the phase margin. As a result, it will lead to a poor phase margin, and that increases the percentage overshoot. It has reduced, very negligible impact on the settling time, but of course, it has impact in the rise time. That means, higher proportional gain try to reduce the rise time, but at the same time it increases the overshoot undershoot. And of course, higher proportional gain can reduce the steady state error, but it cannot achieve 0 steady state error, okay. Whereas, the integral action is used to reduce the steady state error, and if you wait for long time, like limit t tends to infinity, then you can get 0 steady state error, provided that if the input is a step input. But integral action cannot achieve 0 steady state error if the input is sinusoidal or something else, and that comes from the theory of internal model control. Now, for the integral control, because most of the cases that we are going to consider is a step input. So, PID controller, that means integral action, will inherently try to achieve very reduced steady state error or almost negligible steady state error. If we increase the integral gain, then the settling time will increase, because it will be more oscillatory, overshoot will increase, that is because it will reduce the phase margin, okay. At the same time, it will also increase the settling time. But some cases, when we discuss about current mode control, because as well as the voltage mode control, so we discuss about feed forward action. So, if you do not consider feed forward action, in voltage mode control, we will see the loop gain depends on the input voltage. So, in order to, that means the loop gain can vary when there is a change in input voltage. That means, if at lower input voltage, we will see the lower loop gain. In order to anticipate, we need to increase that integral gain, because we need to achieve certain DC gain, and this higher integral gain can be problematic, because it can cause higher poor phase margin. But in analog control, because we design all this PID controller coefficient offline, so it design at the very beginning. but in digital control you can tune it, but nevertheless this integral action, if we increase to reduce that is steady state error, it has an impact in the transient response. Now, the derivative control is used, which is trying to provide more damping, so that it reduces the overshoot because it try to increase the phase margin, and it also try to reduce the settling time because it try to damp the system, right, but it has negligible impact in the steady state error. Okay. Next, we want to discuss what are the different PID controller tuning rule. So, one of the tuning rule that we are going to consider in this particular lecture is PID controller tuning using stable pole zero cancellation, and that is something analytical method, like this is offline method. The second one, PID controller tuning using internal model control, IMC based tuning. I am not going to discuss, but you can refer to standard textbook where these techniques are discussed in elaborate in detail. Another specification is the PID controller using transient specification, and this we are going to also consider in this particular using MATLAB case study. So, we will consider this as well as this MATLAB case study, where we will use a MATLAB toolbox for this particular second case, and there we can specify the transient time, and then based on some optimization criteria the PID controller can be obtained the parameter, and then accordingly those parameter can be imported and we can use that controller, and we want to see the response. Online tuning method, the Ziegler-Niccolo tuning method is a popular method, but the difficulty in this method require, in order to find the Kp, Ki, Kd, that means the controller gain, you need to run the system under critical condition where it will be oscillatory, and that is something not desirable in a power converter because it may lead to the complete collapse of the system or it can damage the devices. In order to solve this problem, the relay based tuning was proposed. This is a very effective technique where we can generate this oscillation by means of a relay feedback, okay, and we will discuss this technique, the methodology in the subsequent in this lecture, okay, where we can use either a on off nonlinearity or a hysteresis nonlinearity to forcefully create oscillation, but control oscillation. From that oscillation we can measure the amplitude of oscillation as well as the time period, and those can be used to get the tuning parameters. Then there are other method of tuning, online tuning using frequency response method, where if you set some gain margin and phase margin, desired gain margin and phase margin, you can actually tune the parameter. Okay. So, this is also online tuning method, and there are multiple paper, because we are not talking about digital control, multiple pioneer works actually are already proposed in this context. So, now we are going to first talk about PID controller tuning using stable pole zero cancellation. So, we want to start with an ideal buck converter, and this is the loop gain plot. In fact, this we have discussed in the previous lecture, that how to obtain this loop gain, right, because we already obtained the modulator gain, we obtain already the control to output transfer function, audio susceptibility, output impedance. In fact, we have verified this model, open loop model, using time domain simulation. That means we have checked with the response of the linearized system and the response of the original switch system, and we have verified that. Okay, that means we have verified the models are reasonably accurate, at least within the control bandwidth, but we have not talked about what is the control bandwidth, how much is the control bandwidth that we can achieve. Okay, so ideal buck converter, this is a loop transfer function, and then if we take a PID controller, ideal PID controller, we are going to talk about the realization aspect, but then what is our objective? Our initial objective, we need to cancel, that means the numerator of the controller, that polynomial, we need to set to the denominator of this plant. Okay, that means what we want, the numerator of this controller S, we want to make exactly equal, but I will discuss if this is a non-robust compensation, and in the next lecture we will discuss if you cannot exactly cancel, then what could be a better way, because the problem in this method LC parameters are reasonably known because they are known from the design, because we have selected L and C, though there can be slight variation like a 10% variation plus minus LC, but resistance is something which varies. So, we do not know what will be the resistance value, right. So, it is not easy to know, because you can use a load estimator, but that is not a good technique. So, that means we need a robust compensation where the load resistance will not come in the compensation process. The another part is the loop transfer function. You see, it depends on two things. One is the input voltage, which we told that is the drawback of this voltage mode control, because the loop gain is dependent on input voltage. And we will show in subsequent lecture when we will compare this dependency of the input voltage in the loop gain can be overcome by considering an input voltage feed forward. Okay. So, by using an input voltage, because we saw in lecture number 14 as well as lecture number, I think it was in 17, where we have discussed the feed forward control along with the feedback, where we can achieve the input voltage insensitive, like a input voltage invariance in the loop gain by means of feed forward. The next part, the loop gain under voltage mode control. So, it is the product of the modulator gain, and modulator gain is nothing but 1 by Vm, where Vm is the maximum voltage of the sawtooth waveform. That means, if I take the sawtooth waveform like this, so it starts from 0 and this is my Vm. Okay. So, this is a modulator gain. GVD is a control to duty ratio transfer function, which is also called control to output, but here duty ratio is the control variable. So, it is a control to output transfer function where the duty ratio is the control input, and this is our PID controller. Okay. So, we can write this, and numerator of the controller we discuss, that means NC, DP, and under perfect stable pole 0 cancellation. So, we can write down from the previous expression that Kp by Ki is equal to L by R and Kd by R. So, if you go back, so previous, so this is we are talking about NC rather than I will say Ncon, it is a NC, right. So, I can just rub this because okay. So, it is NC. Okay. So, now you see this L by R simply Kp by Kr, that means this is my L by R, Kp by Kr, and Kd by Ki is simply Lc. Okay. So, that is what we have said here, but here there are two equations 1 and 2, but there are 3 unknown 1, 2 and 3. So, we cannot solve it, because if there are 2 equations 3 unknown, we can get infinite number of solution depending upon if you choose Ki some value, you will get Kp and Kd. So, you can have a infinite set of values, right. Then the loop transfer function, if you do perfect compensation, because we are cancelling the denominator of this transfer function by the numerator of this transfer function. So, the rest is nothing but this loop transfer function. Okay. Here we are considering this whole thing to be KL, this is my KL, and if we do that KL, the loop transfer function is simply an integrator with a gain, right. And if you take the loop gain, magnitude of the loop gain is simply KL by omega, and if you take the phase, it is minus 90 degree. So, it looks like this, that means this slope is simply minus 20 dB per decade in log scale, like decade. Okay. So, a gain plot, it is because it is just pure integrator, and we have a phase of minus 90 degree. So, as a result your phase margin is 90 degree. So, this phase margin seems to be quite large, because it will lead to overdamp system, because your loop transfer function is a first order system. So, naturally if you want to obtain the closed loop transfer function, it is nothing but our loop transfer function by 1 plus loop transfer function. Okay. And what we will get? So, here it is KL by S, 1 by KL by S. So, we can write 1 by 1 plus S by omega p. So, where omega p I can write 1 by KL. Okay. So, omega p is simply omega p is simply KL, that means if you write it, it will be S by KL, where KL is S, omega p should be KL. And what is KL here? So, we have written here, right. So, it is nothing but Fm V in Ki. That means, now we need to set what is my omega p, that is my design variable. So, it is only one degree of freedom, that means by changing the integral gain, and if we write in terms of time constant 1 by 1 plus S tau closed loop into S, where tau closed loop is simply 1 by KL and which is nothing but 1 by Fm V in into Ki. That means, if we increase the integral gain, your closed loop time constant decreases, so it will respond faster. But now the question is that how far you can increase the Ki. So, at crossover frequency, our gain loop gain magnitude will be 1. From there we can find out that this Ki can be obtained by this, which is nothing but our in radian per second crossover frequency Fm by V in. Okay. So, now the question is that if you want to increase the crossover frequency, you have to simply increase the integral gain, and it is the only degree of freedom which can be used to change the cutoff frequency and which eventually decide the closed loop bandwidth. So, third unknown is here, and Ki can be obtained by setting the crossover frequency, and we want to, for a given Fm Vn, we want to see what crossover frequency we can achieve. But unfortunately, we have used an ideal PID controller which cannot be physically realized. So, in order to solve this problem, we need to consider a high frequency pole with the PID controller. So, which is equivalent to, so this particular term is equivalent to tau d into S, where this was a derivative time constant, right, and I am writing in terms of a pole. So, we are putting a high frequency pole, and if we set this high frequency pole 10 times faster than switching frequency in radian per second, then we can have reduced effect of this pole into the actual closed loop performance, because this is just for sake of implementation of the PID controller. Otherwise, if you use an op-amp, the op-amp itself has a finite bandwidth, and that this bandwidth will be set by the op-amp. Okay. So, we can increase the Ki value and we can check the response, and that we are going to do, because the same kind of structure we will get even for a practical buck converter, and we need to check the model validity. So, this part we hold on, because what we got, our loop transfer function that we obtain here, our loop transfer function that we found, that means here we got the loop transfer function is KL by S. So, we want to see the closed loop performance for varying, and where KL is a function of is proportional to Ki. Okay. The next, we want to use PID controller for a practical buck converter. Now, it is a practical buck converter, okay, where we have considered practical buck converter, we have considered the actual parasitic. That means, you see this alpha is coming. What is alpha? The alpha we know it is nothing but R plus R equivalent by R. What is R equivalent? It is nothing but DCR plus RDS on. This we know. We talked about ESR, the skew factor, and these things we have already discussed multiple times. Now, we want to compensate. So, the loop transfer function of a practical buck converter, where we are trying to design this KC, and we are taking a PID controller. This is a practical PID controller, right, which has a derivative 0 pole, sorry, derivative pole, because sorry, derivative I think filter. So, practical PID controller, and we know this K1, K2 in terms of Kp, Ki, Kd. Now, for this transfer function, if we set the PID controller, that means here again we want to the numerator coefficient we want to cancel with denominator polynomial, and since they are stable, we can do stable pole 0 cancellation. But again, it is a non-robust choice because the Q is nothing but it is a function of resistance, and which may not be a robust solution, and that we will discuss in the next lecture. So, now if you set it, then we have 4 unknown, because how many unknowns is, one is Kp, Ki, that means what are the unknown? We have Kp, Ki, Kd and tau d, because in the first case we have only 3 unknown for ideal, where we kept this to very low, which we do not need to find out, because it can be kept much lower than the, because we have said that the frequency corresponding to this will be much higher than the switching frequency. But here we have 4 unknown, and this is one equation, this is second equation and third equation. So, we have 3 equations. So, same problem. But if we compensate again after this pole 0 cancellation, now we are setting this ESR 0 and this term, that means if we take this term, we are going to cancel with this term. That means we are cancelling ESR 0, which can be reasonably, which is reasonably known by using the derivative filter pole. So, that is a pole 0 cancellation. The controller 2 zeros are used to cancel the planned pole. Okay? So, the rest part is that means if you write the loop transfer function, what is our loop transfer function? Now, after this compensation, our loop transfer function is simply Ki, this Ki, then V in alpha Vm by S, because here we have an 1 by S term, it is coming here, the Ki term is coming here, and this term is coming here. Okay. Now, if we write the frequency response, we replace S equal to j omega, then we are writing Ki V in alpha Vm. So, this is the expression. So, this is same as earlier, except this term is this comes into picture, and if your R equivalent is very small, this alpha will be 1. So, it will be same as earlier. But here we have not considered a derivative, the filter, derivative filter, the pole, we have not, here we have used to cancel the ESR, and since the ESR is very low, that ESR 0 will be at high frequency. So, this is also a high frequency pole. So, they can be used to cancel each other. Then the resultant loop transfer function again becomes a pure integrator, same as earlier, and we can select omega c and Ki from this crossover frequency, because this is at crossover frequency. So, this is omega c is our crossover frequency, right. So, crossover frequency, we can find it out, and now we have to check the model validity. So, let us go to the MATLAB. What we are doing here? Here we are taking again the small signal model, and we have discussed in the previous class that parameter file, we have all these Q calculation, omega 0, all these calculations, we have discussed while validating the small signal model. So, audio susceptibility, open loop output impedance, control to output transformers, everything. The modulator voltage is set as 10 volt, and then this is an analytical method of PID controller design, where cutoff frequency is set to 100 times. It is much lower, but I will show you why I set it. Okay. Then omega c can be computed, because if you go back and you will see that omega c here we are writing, it is nothing but 2 pi f c, right. So, it is coming from here alpha Vm by n. So, it is coming here Ki equal to alpha omega c divided by Fm Vn, and Td, the derivative filter time constant, is 1 by ESR 0, which is omega z here. You see the omega z is used ESR 0. Okay. So, it is a ESR 0. Then we have numerator and denominator. Denominator of this controller is taken as the numerator of the controller is Ki into the dp, that means the denominator of the plant, which is nothing but the denominator of this control to output transfer function. Okay. So, now with this let us simulate, and check. So, this is the response of the system, overdamped system, and we have applied a 0.1 volt reference voltage transient. So, initially the output voltage was 1 volt, now it is changed from 1 volt to 1.1 volt. Okay. Now, we want to see the response, matching response with our small signal model. So, let us run it and we want to verify whether they okay. You will find that the response is not at all matching. Okay. So, there is a significant deviation from your first order model and from your actual response from the small signal model. So, in order to do that, let us do, because we have taken the load resistance to be very low. So, if we take 0.05 at 20 ampere load, that means load. Okay. So, this is the response, and now again we are plotting the same method we are following. Okay. So, since we have increased, so now they are somewhat closely matching, but they are still not matching perfectly. Now, if we reduce further the bandwidth, that means here we set the cutoff frequency. So, if we make 200, it is much slower, and if we run it and if we try to match the response, then you will see they are matching closely. That means this first order model, we cannot go for a higher bandwidth, because this model is no longer valid. You see, it cannot even capture the behavior up to its time constant, because there is a deviation of the actual switch simulation. Okay. So, the model is not perfectly valid, but still it reasonably captured. But if we try to, because we are even setting the cutoff frequency to be 1 by 200 times of the switching, which is very low. Okay. So, it is too low, and if you see the Bode plot, so if you see the all the stability margin, you will see that the stability margin, if you check, the phase margin is 90 degree, crossover frequency is 1.57, that means 15.7 kilohertz, which is too low, right. So, this is something not acceptable. Even with this, we are unable to match the model. Okay. That means our model is not valid. So, whether you take an ideal buck or a practical buck, but a PID controller, if you want to compensate and to obtain a fast order model, it is something is not sufficient. So, if we increase the bandwidth, the model validity is a concern. So, fast order closed loop model is not a suitable solution. Now, so both ideal and practical loop transfer function actually resemble an integrator. Fast order closed loop system expected to be overdamped, and that we got from the small signal model. But if we want to increase the bandwidth a little bit, the system validity remains in question. So, alternative solution need to be found. Now, we are going for the PID controller tuning using transient specification. So, here we are using MATLAB PID toolbox. Okay. So, again the same converter, practical converter, PID controller, but now we are getting, so first what we are doing, we want to obtain GVC, and that means the control to off, because we are trying to find out this PID controller, but we need this whole transfer function, and this we are calling GVC, which is nothing but modulator gain GVD. Okay. So, the modulator gain expression is this and GVD is this, they are practical converter. Then what we have to do? We have to call the MATLAB PID toolbox. So, I am just first telling the summary before we go back to the actual demonstration using MATLAB. So, you have to call this PID toolbox, and this transfer function is defined already, assuming. Then we need to specify the transient time using the MATLAB graphical interface tool, and then we have to import the controller parameter in the skip file, then extract the numerator and denominator coefficient, and then that means numerator and denominator coefficient. Okay. Then find the closed loop transfer function using analytical model loop transfer function, plot the response using our transfer function, and this is a AC response that we know, and we have to add offset because we want to verify with the actual switch simulation. Then we want to draw the frequency response and the Bode plot, and then run the practical switching converter and verify the response. Okay. So, we want to now go for the actual MATLAB simulation. Okay. So, earlier we talked about PID controller design using pole 0 cancellation, but now we want to go for the PID controller design using transient specification using MATLAB toolbox. So, this is the one that we are going to discuss. Okay. This is the so this is the one we are going to uncommon. You can see we need a GVC that we have discussed and PID tool, okay, and then let us run it. So, if we run it, you see it will show error because it enter into the GUI tool and it require this controller transfer function, and do that we have to import from the GUI tool. Unless we import it, this part cannot be executed. So, it is successfully executed up to this part, okay, and we will run the rest of the part once we import the parameter. Now, let us go to the GUI tool. So, here we are going to set the transient specifications. Okay. So, let us try to set the transient specification. Here you can see the time, it is in second, but there is a 10 to the power minus 4. That means, if we talk about 1 into 10 to the power minus 4 second, that means it is 100 microsecond. Okay. 100 microsecond, because if you multiply by 100, 10 to the power minus 6, 100 microsecond. So, we are talking about 100 microsecond and we need to achieve the response. That means, we want to make a bit faster. Okay, we want to make, okay. So, we want to make, okay. So, this is a design, we are tuning this because we are setting the, so this is our, that means we want to achieve the response, that means we want to achieve the steady state response near to this roughly 0.8, that means 80 microsecond. That means, in our case it is like a 40 cycle, like, because 2 microsecond is my time period. Now, we want to import this parameter that I have discussed. So, the parameter, if you see this file, I have called it as gCISO. So, that means we need to copy it and go to this parameter and we just paste it, okay, and we import it. Now, once we import, now we want to run this rest of the file. So, rest of the file I am running. Okay. Now, we obtain, this is the response of the controller which we have designed using CISO toolbox, and we want to see and we want to match. Now, we want to run the converter, okay, because we want to verify whether the converter, now converter is loaded with this PID controller with the parameter that we obtain from the CISO toolbox, the PID toolbox. Okay, let us run it and check whether, okay. So, this is a response I want to show that. So, response looks matching with reasonable accuracy at 3 millisecond that we have applied a transient, and you see we are reaching steady state near about this time. That means, if we reach here around 0.08, that means in 80 cycle which we have set from that CISO toolbox, that means we set 80 microsecond because it is in millisecond. So, it will be 0.08, that means it is taking, if for 10 cycle 1, 2, 3, 4. So, sorry, 20 cycle, sorry, it is 2 microsecond. So, 2 microsecond, here there are 10 cycle, 20 cycle, 30 cycle, 40. So, 40 cycles. So, 80 microsecond means we are talking about 40 cycles that we have already discussed. So, we reach steady state. That means, this behavior is much better than what we achieved in the earlier using exact pole 0 cancellation, because it was 1 degree of freedom control. But here we have designed this PID controller based on transient specification. But if we now, this is designed at very high load condition when the load resistance was very small. Now, suppose we increase the load resistance, now the load current is roughly 1 ampere, earlier it was 20 ampere. So, we have a very good damping. Now, it is with lower damping and we want to run this, we want to design the converter. And you see in this case you have real difficulty with the design, converter design. So, if we want to make that, we have little choice over this. If you want to speed up the response at so this is the response speed and we want to see whether, so this is now we are trying to achieve in this is in millisecond in 2 milliseconds. So, we are making it slower if we make it slow, that means if we try to make it fast, that means if we try to make it fast, like earlier case, we want to achieve in much faster, then there is a penalty in okay, this is one response that we want to achieve, we want to make it fast. Okay, so now we want to again import the controller parameter. So this is a GCSO tool. Let us go to the controller and the GUI tool, and in this tool we want to import the controller parameter. We have imported the controller parameter. Now we want to run it. So we want to run it. Okay. So you can see this is a response of the system, because the response is system has a poor damping and the PID controller is designed. Now we want to run the actual simulation and see what happened. So this is we want to match the response of the converter, and you see the converter response matches quite nicely, but this response is not satisfactory enough, because it is not good enough, because you have to sacrifice the settling time, and if you try to increase the speed of the response, the system will simply become unstable, because you see at 3 milliseconds we have applied load step and it is reaching steady state at 0.3 or roughly at 0.4. That means it is taking around 200 cycles, which is pretty large in terms of transient response. And if we want to improve this response because if you want to make this response faster, that means if you want to speed up, it will simply become unstable, because the similar response we can obtain. So we cannot improve further, because then it will become unstable, because it has a poor phase margin. Okay. So we got a limited response due to this. Now we want to show you that under this condition, if we go for another compensator, that means let us go for another compensator where the same parameter condition at 1 ohm we want to design, because that we will discuss. So PID controller, even we design with cancellation, pole 0 cancellation, we design with transient specification, and first case we found the model validity even at a lower cutoff frequency. In the second case we found the model is very good, is valid, but we have a very slower transient performance as well as the oscillator behavior at particularly what is the problem, because PID controller has a limited flexibility. Now we are going to consider another converter which is called as type 3 compensator, where we want to add one filter. Okay. Before that, let us discuss. So we run this and we found limited degree of freedom because of only one high frequency pole. Compensation became difficult for wide load current range. What could be a possible solution? So we need to consider an extra pole for additional degree of freedom. So if we add one extra pole with a practical PID controller, then it becomes a type 3 compensator which has 2 zeros and 3 pole. One is pole at origin, one is kind of a derivative pole which can cancel the ESR, and the third pole is the one which have a additional degree of freedom, and that we will discuss in the next class, the design method. But this class we want to see what happen if we design this using type 3 compensator. Now in this method we want to design and we want to make sure that we use a different plot color. Okay. So you want to use black color plot. Okay. And in this technique I have designed such that it will ask for bandwidth, since we are operating at a light load. So we have to careful about the phase margin, right. So let us say we talked about like a 20 kilohertz bandwidth, okay, or even maybe 10 kilohertz bandwidth, and phase margin we want to set in 60 degree. Okay. So this is a response which is coming using small signal model, and now we want to verify using our actual simulation. Okay. So this is a type 3 compensator now, and you see using type 3 compensator we can speed up the response significantly, because at the same operating condition the response can be drastically improved, because you can achieve settling time even in 40 switching cycle, which we did it in high load conditions. But in light load we can well damp the system, and this is the matching response of the small signal model and the actual switch simulation. So, this is the second case with the type 3 compensator. They are matching quite nicely, and you can really well damp the system by using this. That means this is possible because we have an additional degree of freedom. So, the type 3 compensator gives an additional degree, and PID controller we have a real difficulty for a wide compensating operating range. So, that means type 3 compensator will be used, and which is nothing but a PID, practical PID controller with an extra pole. Okay. Now, so I have shown you the case study. The better trade-off can be obtained by a compensator, and we will discuss about the design in the next class. Now, here the additional degree of freedom provide to independently adjust both the cutoff frequency as well as the phase margin using these two. So, earlier it was only 1 degree of freedom, where we have only control over the cutoff frequency, but it has a limit. But now, so inaccurate first order model in analytical method, but now with this type 3 compensator we have an additional degree of freedom, and we could achieve much better response. Online controller tuning is relay based tuning that we discussed. This technique can be used in real time. In fact, it has been used in many research paper, probably in commercial product, where the PID controller can be tuned in real time by introducing a hysteresis nonlinearity. Even if you make the hysteresis band very small, it becomes a relay nonlinearity, and that can be enabled before you actually connect the actual. So, this is your actual PID controller, but initially relay is connected and it create a sustained oscillation, and this is your GVC, which include your GVD into modulator gain. Okay. So, step 1, initially relay feedback is connected, and due to this relay action, but you need to make sure that your relay, your DC gain should be sufficiently high, so that you can actually take into the inside the relay band. Then if you start this, that means the input amplitude of the relay should be sufficiently large, and then this technique, the analysis can be carried out using describing function method by using a generalized Nyquist stability criteria, and that we are not going to discuss here. Okay. So, that means using describing function we can get the gain of this particular block, we can obtain the gain. This is for a pure relay where there is no hysteresis, but with hysteresis we will get a complex term, and then by plotting the Nyquist plot of the linear plane and also the Nyquist plot for this the gain of this relay hysteresis term, we can find out the intersection point, and from that intersection point, by finding out what is the phase and amplitude, we can find out the amplitude of oscillation of the, but we have to make sure that it should satisfy the extended Nyquist stability criteria. That means we know that the Nyquist stability criteria, there is a -1 point, and if we talk about any linear transfer function and if it intersect like this, then this is the critical point. So, this critical point, that means if it does not encircle and if there is no unstable pole, then system will be stable. But if it encircle, if the open loop does not have any unstable pole, then it will be unstable. But in case of our relay feedback, along with this this -1, it got changed, it instead of -1 it is -1 by NA, 0, and then we consider the linear plane the Nyquist plot, and the requirement is the intersection. If it intersect, then only there will be possibility of limit cycle oscillation, and that means this -n by A, it can be varied by varying amplitude, and in this case also frequency dependent term, it will be something like this. So, you can actually find out whether there exists a limit cycle, and if it exists, what is the amplitude and oscillation. Then if we find out the control oscillation, we can find out ultimate gain, ultimate time period, and we can find out Kp, Ki, Kd using Ziegler-Nichols tuning method. So this can be used in real time, but limited. The system should not be driven in ultimate gain in a standard Ziegler-Nichols tuning rule. So this can damage the component. In order to solve, the relay based tuning was proposed, and this can be used to generate the control oscillation, and then critical gain can be formulated by 1 divided by this gain, and then we can use the earlier Ziegler-Nichols tuning method to find out the individual parameters of the Kp, Ki, Kd. So with this I want to summarize that PID controller tuning methods are discussed. MATLAB based PID controller design case studies are demonstrated. Advantage and limitations of PID controllers are identified. Digital controller can solve many of these technique problem, because we have considered a type 3 compensator. In digital controller we do not require, even a digital PID controller will have, because it is sufficient to anticipate and the parameter can be adjusted in real time. So that is a suitable candidate for commercial IC. And the small signal based design has a bottleneck for faster transient response. So which also in future subsequent lecture we will see the large signal based PID controller tuning, where the PID controller can achieve, because we are still talking about bandwidth in terms of up to 1/10 switching frequency or even less, but we can go up to the critical limit by setting the PID controller using nonlinear tuning, that we will also discuss. So with this I want to finish it here. Thank you very much.